In the last few sections, we talked about polar coordinates, where we have r as a function of theta, where r is the distance from the origin to the point, and theta is the angle made with the positive x-axis. In this video, we'll discuss areas in polar coordinates. So how do we find the area inside of one of those polar curves? In the Cartesian coordinate system, we used integrals to find areas between a curve and the x-axis. So if you recall, when you took the integral of a function, f of x, then you were finding the area between f of x and the x-axis. When finding areas in the polar coordinate system, we still use integrals, but the area is no longer between the curve and the x-axis. Instead, our formula will find the area of fan-shaped regions bounded by the origin, the equation, and two angles. For example, consider the cardioid r equals 1 minus sine of theta. We call this particular graph a cardioid because it looks kind of like a heart. So if we graph the equation r equals 1 minus sine theta, if we were given the bounds 5 pi over 4 is less than or equal to theta, less than or equal to 7 pi over 4, then what we would do is we would have those two rays at theta equals 5 pi over 4 and theta equals 7 pi over 4. And what we would be finding the area of is we would be finding the area inside the curve between the rays at 5 pi over 4 and 7 pi over 4. So it's basically like a slice of pie or slice of pizza, and we think of that as a fan-shaped region defined by our function and the two theta bounds. Now the way we're going to find that region is similar to Riemann sums. So what we do is we divide the region into a bunch of little slices, but instead of having rectangle slices, they're like little pie slices. So it's the wedge of a circle with angle d theta, so some very small theta angle, and we will add up the wedges to find the total area. So our concept is similar to Riemann sums. We're just using wedges of circles instead of rectangles. Now the area of the fan-shaped region between the origin and the curve r equals f of theta, where theta is between alpha and beta, is a equals the integral from alpha to beta of 1/2 r squared d theta. So here's where this comes from. The idea is we add up infinitely small wedges of a circle with radius defined by the function r equals f of theta. Now delta A, so a small piece of area, is equal to pi r squared, which is the area of a circle, times delta theta over 2 pi. So that's telling us what fraction of the circle we have, because if our angle is theta and we divide by the full radians of a circle, which is 2 pi, that gives us the portion of the circle. So pi r squared times delta theta over 2 pi. So the pi's cancel, and I'm left with 1/2 r squared delta theta. Now think of making those little pieces of angle infinitely small, and then taking the limit as the number of little slices goes to infinity, and that's exactly what an integral is. So we end up with dA equals 1/2 r squared d theta. So to find A, our total area, we're going to take the integral of both sides. So that's where we end up with our formula A equals the integral from alpha to beta of 1/2 r squared d theta. So this formula is what we're going to use. The r squared, remember r is a function of theta, so you're actually going to end up with some function of theta squared. You'll need two trig identities for this section, and these are on your formula sheet. Sine squared of theta equals 1/2 minus cosine of 2 theta divided by 2. And cosine squared of theta equals 1/2 plus cosine of 2 theta divided by 2. So notice they're basically the same formula, except when you have a sine squared, it's subtraction, and when you have a cosine squared, it's addition. And notice that you're doubling the angle. So in order to reduce the power, you double the angle. So you get 1/2 minus cosine of 2 theta over 2 when you're switching from sine squared, and 1/2 plus cosine of 2 theta over 2 when you're switching from cosine squared. So here's our example. We want to find the area enclosed by one loop of the 4-leaved rows r equals cosine of 2 theta. So we have our graph. It has 4 leaves, and they're basically, you have one on the positive x-axis, one centered on the negative x-axis, one on the positive y-axis, and one centered on the negative y-axis. So we have a lot of symmetry going on here, which we might be able to use. But first, we need to find bounds. So what I like to do is figure out where my graph starts. So I say when theta equals 0, r equals cosine of 0. So that tells me that r equals 1, because cosine of 0 is 1. So that means I'm out on the positive x-axis at theta equals 0, r equals 1. So that tells me that's where my graph starts, is kind of at the end of that first loop. And now I want to figure out, when do I get back to the origin? So when does r equal 0? So I take my function and set it equal to 0. Cosine of 2 theta equals 0. And I think about, on my unit circle, when is cosine equal to 0? Well, since my angle is 2 theta, I'm going to have 2 theta equals plus or minus pi over 2. It also happens at plus or minus 3 pi over 2. And to generalize, I could write this as pi over 2 plus or minus n pi, where n is an integer. Now I want theta by itself, and so I'm going to divide both sides by 2. So I get theta equals plus or minus pi over 4, or plus or minus 3 pi over 4, and to generalize, pi over 4 plus or minus n pi over 2, where n is an integer. So coming back to my graph, I know that I'm at the origin, r equals 0, when theta equals pi over 4, and then the lower half of my loop, I could think of that as negative pi over 4 and r equals 0. So if I wanted the entire loop, I could go from theta equals negative pi over 4 to theta equals positive pi over 4. So I want one loop, and instead of going from negative pi over 4 to positive pi over 4, which would be perfectly valid, I'm going to use the symmetry. So I know that theta equals 0 to theta equals pi over 4 is half a loop. It's the half that is right on top of the positive x-axis. So area of one loop is going to be 2 times, and I'm multiplying by 2 since our bounds are for half a loop. So 2 times my formula, 1/2 integral from 0 to pi over 4 of r squared d theta. So remember, that's just the formula for area, 1/2 alpha to beta of r squared d theta. Now I plug in my function r, which is cosine of 2 theta, and I get the area of one loop equals the integral from 0 to pi over 4 of cosine squared 2 theta d theta. And this is because r squared is going to be the cosine of 2 theta quantity squared, which I can just write as cosine squared of 2 theta. And notice that the 2 and the 1/2 canceled each other out. So because I'm using that symmetry, I ended up getting rid of the 1/2. Alright, so now we have to evaluate this, and I rewrote it here. Area equals the integral from 0 to pi over 4 of cosine squared of 2 theta, d theta. And now I'm going to apply my trig identity. So remember, my trig identity says that cosine squared of 2 theta is going to equal 1/2 plus cosine of 4 theta over 2. So I double the angle, and because I started with 2 theta, I have cosine of 4 theta now. So the area is equal to the integral from 0 to pi over 4 of 1/2 plus cosine of 4 theta over 2 d theta. Now, if you're comfortable with integrating this and recognizing what the integral will be, that's fine. If it's been a while since you've done this, you might want to use a u sub for the integral of cosine of 4 theta over 2 d theta. We would let our u equal 4 theta. Then we would have the integral of cosine of u over 2, and du is going to be 4 d theta, and so solving for d theta, I get 1/4 du equals d theta. So to replace the d theta, I'm going to write 1/4 du. So now I have the integral of cosine of u over 2 times 1/4 du. And the integral of cosine is sine, so I get sine of u over 8. Plug my u back in, and I get sine of 4 theta over 8. So anytime you have the cosine of a number times theta divided by 2, you end up with sine of whatever that angle is, 4 theta in this case, divided by the 2 times whatever number was attached to theta. Okay, so now this gives us the area is equal to 1/2 theta, because of that 1/2 in my original integral, plus sine of 4 theta over 8, which we just showed how we got that with the u substitution, evaluated from 0 to pi over 4. So now remember, we plug in our upper bound and our lower bound and subtract. So we'll have area is equal to 1/2 times pi over 4 plus sine of 4 times pi over 4 divided by 8 minus 1/2 times 0 plus sine of 4 times 0 over 8. So this was my f of b minus f of a that you always do when you're taking an integral. Now the 4 times pi over 4, the 4's cancel, so I just get sine of pi, which I know is 0. And then over in the f of a, 1/2 times 0 is 0. Sine of 4 times 0 is just sine of 0, which I know that's equal to 0. And so really I just am left with the 1/2 times pi over 4. So pi over 8 square units is the area inside of one loop of that 4-leaved rows. Now if I wanted the entire rows, I could just multiply this by 4, because I know there are 4 leaves. And notice that we would have gotten the same result if we had used the area equals 1/2 times the integral from negative pi over 4 to positive pi over 4 of cosine squared of 2 theta d theta. So if I use the bounds for an entire leaf, then that 1/2 would come with me throughout the calculation. It would not cancel out. But I would get pi over 8 for one leaf in the end. So in the next video, we'll talk about how to find area between two polar curves.